Well, welcome back. We're in section 4.6 called Newton's method. Now, Newton's method is a formula to help you find the zeros, roots, x-intercepts of a function. It's named after Sir Isaac Newton, our founder of our calculus. You must first set the function equal to 0 before applying the formula. Now, to remind you of what's going on here in terms of roots, zeros, or x-intercepts, you have some function, f of x. And if you graph that function, that graph could come in here and look something like this, maybe something like this, and so forth and so on. So there's your function as you graphed it. Now, what the method that we're doing here is this. This Newton's formula reiterated method is a method that actually allows you to find the x-intercepts, the roots, the zeros of a particular function. It's where the function equals 0. This formula is going to help you figure out these methods, these particular points. Now, this is an iterated formula. Now, what you need to do this formula, and this is pure memorization, the formula for Newton's method is x sub n plus 1 equals xn minus f of xn divided by f prime of xn. Now, again, you've got to memorize this thing, so remember, it's the function divided by its derivative. Now, what you're doing here is this. If I was interested in focusing on this particular part of the function, so I know it comes in here and does something like this, comes in there and keeps on going. I'm trying to find this particular point. Well, your first guess is going to be the little x0 guess. This will be your first guess. And what Newton's method does is that you get the functional value, which is up here at a y coordinate. It applies the derivative to it. And what this thing does is it applies the formula with the derivative and then kind of gives you, based on this formula, your next guess. It'll be your x1 guess. So it plugging the formula at x0, the formula gives you your next guess, x1. So you plot x1, the functional value, and the derivative, and that gives you to plot x3, so x2 there. x0, that'll be x1, then x2. And what's going on here is that this method helps you zero in on exactly where the root is going to be at. Okay? So, to start an example of this thing, to show you what's going on here, I've decided to help you guys out by setting up this little chart. This chart is actually very helpful. So, it says this, starting with x0 equals 2, find the third approximation, what we call x3, to the root of the equation x cubed plus 5x minus 12 equals 0. Remember, with Newton's method, you're finding the solutions, the roots, the x-intercepts, the solutions to where a function is equal to 0. So here's my function, which is x cubed plus 5x minus 12. And I need my derivative, so my derivative would be 3x squared plus 5. And now I'm going to use this to basically use my iterated method. Iterated meaning I'm going to do plug in a guess, and then when I do one guess, it'll crunch out through the formula and give me my next guess. And I'll do this till I get x3. So x0, they told me where I'm going to start. There's my initial guess, was at 2. So now I need f of 2. So to get f of 2, I'm going to do exactly what you think I should do. I'm going to plug 2 into my equation, 2 cubed plus 5 times 2 minus 12, and I'm going to use my handy-dandy calculator to do this to let you know I'm actually off the screen here doing it, plugging in my calculator, but double check along to make sure that you are actually getting the exact same numbers as I do when you plug this thing in. So, and when I plug in 2 into this thing, I got 6. Just double check me. 2 cubed is 8, plus 5 times 6 is 30. That'd be 38. Minus 12. Let's see here. Oh, excuse me. Plugging in 2. 2 cubed is 8. 5 times 2 is 10. 10 and 8 is 18, minus 12 is 6. Now, I can do it with a calculator, but I actually I plugged it in on the calculator. Now I'm going to plug 2 into my derivative. When I plug 2 into my derivative, I got 17. You can do without the calculator, but we're going to go decimals on this thing pretty quick here, so the calculator is definitely needed in this particular section. 2 squared is 4, times 3 is 12, and 12 plus 5 is 17. But now, here's the big deal. To get your next iteration, see this when n was equal to 0, so n 0 plus 1 is 1. So my next iteration, which is my x1 iteration, would be x0, which was 2, minus the functional value, which is 6, divided by the derivative, which is 17. So just to show you I am really doing my calculator on this, it'll be 2 minus 6 divided by 17. And again, what a surprise, classic decimals. So I'm getting 1.647058824. Okay, kind of ran out of room there, but that's okay. We're gonna, and that'll be your next iteration. So this will be the next number that I plug in. So x1, my first iteration, the x0 is your guess. This will be the first iteration after iteration meaning we plugged it into the formula just one time. This was 1.647058824. Now I want to find the functional value of this. So I want to plug this number, using the help of my calculator here, into my function here. So when I do that, I get this. Double check me here. 8824.
Is that working?
Okay, so when I plug in my number into my calculator, I get this point for my functional value, 0.7034396. Double check me on that one. And when I plug it into my derivative, I got 13.138408. And so now my second iteration would be equal to, again, typing it on my calculator, but I want to show you what I'm actually doing on my calculator here. I'm going to do x0, I'm sorry, in this case x1, it'll be x1, which is 1.647058824, my x0 number, minus the derivative, 0.7034396, divided by 13.138408, and that gives me my next iteration, 1.5935181101. There's my second iteration. Now, one thing I want you to notice here is this. Every time I do an iteration, we're looking for the zeros of a function. This is your clue that you're on the right track. So when you plug it in, the number for f of x should be going towards 0 because that's what we're trying to find the solution for. So now, plug in x2. That'll be my x2 is going to be 1.5935181101. So now, I'm going to take that number and plug it into my functional value. And when I plug it in, double check me on this, but this is what I get. I got 0.01401.092. Notice it's getting very close to 0. And when I plug it into my derivative, I got 12.6179. Close enough. Now, and then for my third iteration, I'm going to, once again, show you on the calculator here. Okay, I'm going to take that point, I'm going to take x2, which is my 1.5935181101. I'm going to subtract off the functional value, 0.014011092, divided by the derivative, 12.6179. That gives me my third iteration, 1.5924 0.07701. And that's my third iteration, which I'll put down here, 1.5924077701. And notice that's the third time I ran through my formula. But remember, the question is, what is x3? And that's where I stop at. I want 1.5924077701. And that is my solution. Now, a couple of things you should note, and this is why I like the chart work, so you can see to make sure you're getting in the right answer here. This is the idea. We're looking for this particular very hard function here. F of x equals x cubed plus 5x minus 12, and we're trying to set it equal to 0 and find the solution for it. So we have an idea where we think this x-intercept, root 0, actually is, and that's my x0 guess. By applying Newton's method formula, I plug it in, and it zeroes in, and it gives me my next iteration or my next guess. So they take my next guess here and rewrite him and then plug him into the formula. Now I do this several times, and this is the whole idea. What's happening here is my functional value should be going down towards 0, because that's what we're trying to find, where the functional value equals 0. And the more times I do this, this should be zeroing in on the answer. And here's my group of answers right here with x1, x2, and x3. And after a while, the number should start repeating. It should be zeroing in right on top of a number. And notice 1.59s ends up repeating. So I know I'm on the right track. This is the root, the x-intercept, the 0 of my function. It's the solution when the function equals 0. Just applying Newton's method the third time. And this is a process that, again, computer science and computer programming and stuff gets into, because I can do this many, many times, and the more times I do it, the closer this thing is going to be to 0, and the more decimals this thing's going to start repeat, and that's a clue that I'm on the right track. So let's try another one of these. All right. Starting with x0 equals 0, they always give you the initial guess, that way we're all starting out on the same foot. Find the second and third approximations to the root of the equation e to the negative x equals 5 plus 7x. Now, the first things first, we're trying to do Newton's method on this thing, which is our formula that you have now memorized. Here's the deal. You got to find the function, and the function is got to be set equal to 0, because this formula finds the zeros, the roots, the x-intercepts of functions. It finds where the function is equal to 0. So the first thing you should do is set your equation equal to 0. So I'm going to subtract 5. I'm going to subtract 7x. That's going to give me e to the negative x minus 5 minus 7x, and that's equal to my function, because that will be set equal to 0 when you pull everything to one side. And now I need its derivative, so apply calculus here. Derivative e to the negative x is e to a function. Derivative e to a function is e to a function times derivative of the exponent. Or so the derivative of e to the negative x is e to the negative x times negative 1. And I'll put the big negative out in front. Derivative of minus 5 is 0. Derivative of minus 7x is just minus 7. So there's my derivative. So, once again, using my calculator to help me plug numbers into this thing, because you are going to be going decimals on this. So having calculators is going to be very advantageous on this particular material. So my first iteration, my 0 iteration, which is my guess, is 0. So now I'm going to plug 0 into this function. That shouldn't be too bad here. Let's see here. E to the negative 0, well, e to the 0 is 1. Minus 5 is negative 4. 7 times 0 is 0. So 1 minus 5 is negative 4. Plugging it into the derivative. When I plug in the derivative, e to the negative 0, e to the 0 is 1. That'll be negative 1 minus 7 is negative 8. So now, plugging it into my little formula here, now I'm just going to go ahead and, I guess, put my calculator down and show you what I'm doing here. Remember, this one's the easy one, so this will be your next iteration up. This was the 0 iteration of the guess, so the first iteration would be the iteration before that, which was 0, minus the functional value, watch your signs, minus negative 4, over the derivative, negative 8. I really don't need a calculator for this, but I'm going to do it anyway. Just when you use the calculator, remember, be careful, don't screw up because of the sign. So I've got 0 minus negative 4 divided by negative 8. Now if I did this in my head, a negative negative is a positive 4 divided by negative 8. Positive divided by negative is a negative, and I get negative a half. Yeah, and they did too. Negative 0.5. Okay, so now my first iteration after my initial guess is negative 0.5. Now this is going to be more nasty with decimals on the calculator here. So now with decimals on the calculator, I'm going to start really using my calculator to plug numbers in. So for my functional value, I'm going to plug in negative 0.5. And when I do that, I get the number 0.14872,127. Plugging negative 5 into the x for my derivative, plugging negative 5 into my derivative, I get negative 8.648721. And now for my next iteration, slide it up, you guys can see this. That'll be my second iteration, would be the first iteration, negative 0.5, minus the functional value, 0.14872,127, divided by the derivative, negative 8.648721, close parentheses. And so my next iteration is a negative 0.482804. 247. Okay, so that'll be my next iteration. Just recopy that number, negative 0.48280427. Now I'm going to plug that into my function, and using my calculator to do so. For my functional value, I got 0.0002425.6. Actually, on my calculator, I got 2.4256 e negative 4. E negative 4 scientific notation. It meant I moved my decimal place 4 places to the left. That gave me 0.0042. I'm sorry, 0.0002425.6. And now I'm plugging into my derivative. I got negative 8.620613. And now plugging it into my function, my iteration formula for x3. This will be my functional value, negative 0.428280427. My functional value, my second iteration, minus my functional value, parentheses, 0.0002425.6 divided by negative 0.620613. And again, all this is multiplying, dividing, and adding, and I get the number negative 0.4824134.306, and that becomes my third iteration, negative 0.4824134.306. A couple of things before we finish this problem is, notice my function value should be going towards 0. They are. Notice my my decimals, once I do my iteration, should be repeating. You should be zeroing in on the same number. Looks like I'm pretty much got it down to the negative 0.482, and then more iterations I do, the more things are going to start repeating. Also, your derivatives will start repeating after a while, because at that point the derivative happens to be the same. So the numbers should all start repeating is going to be the big key to this thing, and the functional value should always go to 0. There's a check for you. But remember the question. The question was up here, find the second and third iterations. So to answer the question, the second iteration was negative 0.48280.427, and the third iteration was negative 0.4824134.306, and that would be my solution. So it's not a hard process. However, it takes some time, and it's very calculator, add, subtract, multiply, divide prone. But it's a wonderful way of zeroing in on the answers. Now, third one here. And this is going to be the hard part about this particular problem when you start doing these web work problems and what your professor is going to be doing in class with you guys in terms of applying this Newton's method formula would be something like this. Find the equation f of x that you would use Newton's method to solve this, the fifth root of 17. We want to basically use this method to find what the fifth root of 17 is. But to do that, remember, Newton's method requires a function, and then it's going to require a derivative and an initial guess from your part. So you had to figure out what the function is. But here's the trick. To figure out a function when you're trying to approximate a number, this is the trick. You set x equal to the number that you're trying to calculate, the decimal version of. X is equal to the fifth root of 17. Now you're going to work backwards to create a function where this was the answer. Well, what gets rid of a fifth root? I'm going to sit there and try to pull everything to one side. So I would take the fifth power to both sides because fifth root and the fifth power cancel. This leaves me x to the fifth equals 17. But remember, the function for Newton's method must be set equal to 0. So I'm going to subtract 17 from both sides. That gives me x to the fifth minus 17 equals 0. Newton's method finds where functions are equal to 0. Therefore, my function must be x to the fifth minus 17. Now, there's your function. Take its derivative. Do an initial guess. What do you think approximately the fifth root of 17 is? And then use the iteration method to actually get this thing to zero into the answer and give you an approximate number. But this is the trick of how to go from an answer to what the function must be, so you can actually use Newton's method formula to approximate this thing going decimals. Hope that this has been helpful, and I'll see you on the next video.